Welcome to 6004, Spring 2016 edition. My name is Chris Terman, and I, along with Silvina Hanono-Wachman, will be your lecturers this term. As you can see, we have a bit of a video set up and stuff. As you'll discover, I like online. And so all the materials are available online, all the assignments you do with your browser online. Pretty much everything you need for 6004 is online. On the other hand, when I was a student, I loved going to lecture, and I actually like giving lectures. So I hope at least a few of you will decide to come and see it live. But we will attempt to post videos of the lectures online, usually in the evening of the day that they're given, assuming, of course, the video gods don't hear me and decide to have a joke. So the website is pretty simple. It's 6004.mit.edu. It's convenient to use a browser that has your certificates, because then the server doesn't demand that you log in. It will know who you are. You can get all the handouts online. You can get tutorial problems that sort of help you understand what the take-home message is for each lecture. And that's also the purpose of the recitations, which are Wednesdays and Fridays. And in general, the recitations match up with the lectures. So you have a chance to sort of see some problems being worked, ask questions in a more intimate setting, and I would say that a lot of students feel that recitations are a key to their success in 6004. We have a bunch of information there about the course staff and our grading policies and late days and all of that you can find on the course info page. Please go there to read it for yourselves. The big thing I want to point out is Piazza. Okay. We make a lot of use of Piazza in the course. You have any questions, if you email me, I'll encourage you to please instead post in Piazza so that I can answer each question once instead of 300 times individually. Last semester we had over 1,000 posts. I typed in about 1,500 answers, responses. So it turns out if we collaborate on making that an effective communication forum, I think you'll discover that you get quick response and good answers to your questions, and you can help each other out too. And in fact, I encourage that. We do ask that you come in to get checkoffs for your labs to the 6004 lab. Plus, we staff it in the afternoons and evenings in case you want to come by and get some one-on-one help. The lab is 32083. It's actually just right around the corner here, just out this basement door, and keep hanging a left or two, and you'll walk right by it. It's across from the physics steel classroom. It does have a combination. So let me tell you what the combination is. I can't tell you, I'm on video. I'll write it down. But it's on video too. Well, hell. Everybody in the world knows this combination. So if you happen not to remember it, just ask anybody who walks by and they'll say, oh sure, it's not a very well kept secret. So you should be able to get all your answers about mechanics and questions about mechanics and stuff on the info page. If not, post on Piazza and we'll be happy to answer your question there. Just in case anything that somebody's dying to know the answer to, meaning of life? No. About mechanics of the course. Good time to ask? No? Okay. Alrighty, so what does 6004 cover? That's an interesting question. You may have all heard of the notion of, whoops, I've skipped past the important part. You may have all heard of the notion of a full stack developer. That's somebody who can sort of handle all. So in 6004 we have a pretty full stack indeed. We start with Atoms and we end with Amazon. We cover a lot of ground in 6004. In fact, we pretty much cover all the material starting with digital circuits on up. So we'll be making sort of a bottom-up traverse here through all of these topics. And you'll notice that we sort of alternate between talking about the building blocks themselves, a digital circuit or a finite state machine or the operating system, and separately talk about the abstraction that we're trying to create by assembling the building blocks to implement a particular piece of functionality. So the abstractions are all sort of written in red. And you can ask yourself, what's the most important part of this? I mean, should I be concentrating on the building blocks or the abstractions? And, since it's a rhetorical question, I'll go ahead and answer it. The answer is, not surprisingly, both. As it turns out, the abstractions are very long-lived. This notion of logic gates, when I first got into logic in the 60s, some years ago, I had a TTL data book that told me what logic functions I could buy from the local logic supplier in terms of these little, a whole integrated circuit had 4 gates in it. This was pretty high tech. Anyway, the list of gates in the TTL data book and the list of gates in the standard cell library that you are going to be using to design your 32-bit RISC machine, okay, are in fact very much the same list of gates. So the abstractions are timeless. And so they're well worth understanding because even though the technologies may change, okay, the abstractions will serve you well and help insulate us from future changes in the technology. So the corollary, the good abstractions really are a super important part of doing engineering. They allow the technologies to evolve. In other words, I can come up with a new family of logic gates in terms of, say a new set of devices that implements a family of logic gates, and pretty much preserve all the higher levels that are based on higher level abstraction. I don't have to go rewrite my programs, every time Intel issues a new processor. And that's really important to sort of keep our technology engine moving forward at a great rate. So the other thing that we discover is that at each level we only have a small set of building blocks, and although the devices at this level are huge, right? I mean, we're talking about multiple cores, each of which has billions of transistors. We're able to design, small engineering teams are able to design them because they don't design them at the level of atoms or individual devices. They design them using mechanisms at higher levels of abstraction. So the abstraction helps us, first of all, sort of grasp the complexity of the design and sort of manage it through many levels. Plus, it insulates us from future technological changes. And so both of those are important things for us as engineers to learn how to do and to learn how to sort of paint within the lines that the abstraction offers so that we're afforded those guarantees moving forward. Okay. So that's sort of a very quick soup to nuts of what we're going to cover. Our first topic is information. Okay, since we're designing a machine to manipulate and transmit and store information, let's spend the rest of this lecture talking about what is information. To be a good engineer, you often have to have a good metric, a way of measuring, how the goodness of whatever it is you're designing, is it meeting its goals? And that's true. If we're going to build a machine that manipulates information, we need to be able to measure information and sort of evaluate whether our scheme for representing and manipulating information is in fact good. So information resolves uncertainty. That's the way, so it's data communicated or received, okay, that resolves uncertainty about a particular fact or circumstance. So that's that's going to be our engineering definition of information. Here's an example just to give us a hands-on thing. So I have slides here. I'm going to be doing some writing, filling in some answers and stuff. Do your neighbor a favor and wake them up when it's time to write in an answer just so that they don't lose track. Or ask your neighbor to help wake you up if that's really the issue. Okay, so I'm proposing that we're going to draw a single card from randomly from a deck. And I'm going to send you one of 4 possible messages, labeled here A through D, that tell you something about the card that I've drawn. And I'm interested in evaluating how much information is conveyed by each of those choices. So if I tell you the card is a heart, how much information has been conveyed? Well, so information resolves uncertainty, so we want to ask ourselves the question of how much uncertainty has been resolved. If I tell you it's a heart, how many cards, it started off, it could have been any one of 52 cards. If I tell you that it's a heart, I've narrowed that down to how many cards? 13. Okay, so let me write down 13 here. Alrighty, how about if I tell you the card is not the ace of spades? I've left you with 51 choices. So that's actually a fair amount of uncertainty has been left in that case. The card is a face card. In other words, it's a jack, queen, or a king. How many of those are there in a deck? There's 12. And here's that fact of the day, the thing that you'll remember long after you've forgotten the rest of 6004, which is, what is the suicide king? That's the king with a sword through his head. See, I bet some of you probably didn't know that. I see a sign back there. I don't know. Okay, so the question is, how many of those are there in the deck? Are there 2? Oh no, I think there's 1. I think it's always the King of Hearts. So, okay. So which of these messages resolved the most uncertainty? Which one, sort of narrowed it down the most? Which one gave you the most information about the secret card I haven't shown you yet? Well, message D is the one that resolved the most uncertainty. So that's the message that conveyed the most information. Okay, that's okay. And what message resolved the least information? B. Okay, so you sort of get the idea here. When you're trying to figure out how much information is involved, you need to figure out basically how much uncertainty has been resolved. Alrighty, so the way a mathematician would model this is with as a random variable which has n possible values, x1 through xn, and each one of those values has the probability p1 through pn of occurring. If I run an experiment and choose a value for the random variable, it'll be one of the values from x1 to xn, and the probability of choosing a particular value is given by the p sub i's. So what I want to do now is, using this sort of mathematical formulation, write down a formula which tells me how much information, okay, I get. So first I need to sort of characterize the amount of uncertainty. Well, that must be related to the probabilities, but how is uncertainty related to the probability? There's uncertainty for a particular choice. In this case, I'm asking for the information that when you learn that x sub I was chosen, how much information did you get? I'm interested in figuring out, first of all, what's the uncertainty associated with x sub I in terms of p sub I? Just sort of intuitively. If x sub I was very probable, would you say it would be uncertain that I would have x sub I, or that it would be actually not uncertain at all? It would be pretty likely I would get x sub I. The second one. Good. Short and sweet. Okay, so here we go. So I claim that the uncertainty is proportional to 1 over the probability. Okay, the greater the probability, the less the uncertainty. And now to actually turn that into a measure, I sort of want to take the magnitude of that. And the time-honored way is to go off and do the logarithm to determine the magnitude of that quantity. And notice it's the logarithm base 2. And that means that we're measuring information in bits. So the unit of information is a bit, and the way we associate information with the likelihood of a particular message being sent, or the amount of information conveyed by a message, is inversely proportional to the probability that that message would be sent. So a highly probable message conveys little information. The sun will come up tomorrow. Okay. I probably almost certainly knew that. And I would say that you haven't really told me anything new. There was almost no uncertainty there. If I said the sun will not come up tomorrow, you say, you should probably print that in a huge headline and let me know, because that's actually very unlikely, and I'm actually very interested in knowing about that. Okay, any questions about our formula for the information content in a particular message? We're going to take that basic definition, though, and parlay it into some interesting observations about how we encode information. Okay, so what happens when a message doesn't resolve all the uncertainty? In other words, I've given you some data. I've told you the card is, say, for example, a heart. Okay, but I haven't told you exactly what the card is. I've only told you a little bit about what the card is, some information about the card. And what I've done is I've taken the probability that's the heart, which in this case is 13 over 52, and I've used that in my information formula to tell you that the information involved in sending the message that the card is a heart is 2 bits. Now, I find that super satisfying. Now, why do I find the answer 2 bits so satisfying? I don't know, you're weird, Chris. Only an MIT person could find the number 2 satisfying. Yes? It's an integer, okay. We'll discover in a moment that there's no basic constraint that information content be an integer. We'll ask ourselves what that means. But here there's sort of a different thing. I'm thinking about how I'm going to encode information. Yeah, in the back. Right, so there's 4 suits, right? There's heart, diamond, club, and spade. And so it would actually take us 2 bits. I could come up with a 2-bit encoding, 0001, 1011, to convey which of those things. So in some sense, the amount of information conveyed by this is telling us a lot about maybe how we should encode that message in a way that is the most efficient way possible. Okay, so keep that in mind. We'll come back to that argument in a second. A very common case is that we started off with n choices, and I've narrowed it down, n equally probable choices. That's a standard scenario in the situations we're interested in. If I'm sending you a message that's full of letters, without any other information, or say full of numbers, you might say, well, the numbers are all equally probable. Right? 1 is as probable as 7 in the messages I would be sending. Without anything else, knowing anything else, you would just assume digits would be equally probable. I give you some information. It's odd. And I'm asking you how much information has been conveyed. So I'm going from n choices, equally probable choices, down to m choices. And we have a formula. We can just apply the same formula from above. And there's actually, just to write it down more explicitly, log base 2. I'm just doing a little bit of arithmetic for you here. Log base 2 of n over m is the amount of information contained. So I'm really just reusing this formula. In this case, the probability of getting that information that partially resolves the uncertainty is m times you have m different choices it still can be, and each one of those choices has probability of 1 over n from the equally probable choices of occurring. Okay, questions about that? Again, it's log base 2 of that. Lots of examples on the next slide. We'll work through some things. Okay. Information involved in a coin flip. How many choices are there before I flip the coin? And at least if you assume coins don't stand on their edge or something, sure. 2. If I tell you the result of the coin flip, I've narrowed those 2 choices down to 1. What's the information content? Log base 2 of 2 over 1. Which happens to be 1 bit. Ooh, another satisfying result, because we can obviously encode the results of a coin flip using 1 bit, 0 for heads, 1 for tails. This engineering thing seems to be working out pretty well. We have a measure here that makes sort of intuitive sense. Okay, a card drawn from a deck is a heart. Well, we've sort of done that. There are 52 cards to start with, 13 hearts. The information content is log base 2 of 52 over 13. Which is 2 bits. Suppose I have 2 die, a red die and a green die. So each die has 6 faces, so there's 36 possibilities. And when I tell you the result, the red was 3 and the green was 4, I've narrowed it down to 1 choice. What's the information content there? Well, you get the idea. Log base 2 of 36 over 1, which is equal to 5.17. Ooh, it's not an integer. 0.17 bits? Mr. Blue wants to know. So, help me out here. What are we going to do? What's that 0.17 telling us? How would it help us with our engineering? Yes?
You can't encode it in 5 bits, but like 6 is a little overkill.
So 5 bits, clearly if I sent you 5 bits, there's some possibility, there's only 32 choices, and so there's some choices I would have to double up the encoding for. So I have to send 6, so it's a bit of an overkill. When might I take advantage of that 0.17? Yeah?
On average, if you're trying to convey the message, it might sometimes take 5 bits, and sometimes it might take 6 bits, and so this is the average of the number of bits.
True, although if you and I are sending messages back and forth, since you won't know what's receiving, you wouldn't know whether you expect 5 bits or 6. We'd have to agree on something like 6 bits. Suppose I wanted to send the results of 1,000 coin flips. How many bits of information would it take? Would it take 6,000 bits because we've agreed that we have to encode a single flip with 6 bits? What is this information telling us? It seems like we should be able to find an encoding. Maybe we can, maybe we can't. But the information content would be 5,170 bits. So what we're discovering is that fractional bits tell us what will happen if we have to send many, many, many messages. And perhaps we can find some more efficient encoding that takes advantage of the economies of scale. Okay. Alrighty, so here I've basically filled in the table from the first page. So these were choices A, B, C, and D. Okay, we see all the probabilities and the information, and we can see that, as Mr. Blue was pointing out, that these numbers here pretty much corresponded with exactly the ranking we came up intuitively. So our measure is sort of lining up with the way we hope things would work. Okay, so that's our notion of information content. We're going to introduce a notion of entropy, which is the expected information content. So I've been talking about the information content in a particular message. Now I want to tell you about the information content on the average. Well, how do you compute an average? It's actually not so hard. So you always sum over the probability. So all the different, we're going to take all the different possible values of the random variable x, and there are n of them. Okay, we're going to multiply each value by its probability of occurrence, and the information we're interested in average, the information we're interested in averaging, I'm better at one-syllable words, I guess, is the information content. And the information content for choice sub I was log 2 1 over p sub I. So this expected value of the information content is called the entropy. And we'll see that it serves basically as a measure. It'll help us figure out what good encodings are if I have to send you a lot of messages about the result from choosing messages from that set of messages that are represented by the random variable x. Okay, so here we go. Here's the 6004 grades. We almost never give Fs, so that's the good news. A, B, C, and D, here's the probabilities. These are completely bogus probabilities. The probability of an A in 6004 is quite high, particularly if you put in the work. And so I've computed log base 2 of 1 over p sub I for you. Okay, and now I want to compute the entropy. I'm not going to write this out by hand because it would take me too long and you might not be able to read it. Okay, so 1.626 bits. That's the entropy associated with sending messages drawn according to these probabilities from the set A, B, C, and D. Okay, so now we're going to evaluate possible encodings, bit level encodings. We're going to actually come up with bit strings to represent A, B, C, and D, and we're going to evaluate the expected value of messages sent using the encoding with what the entropy tells us. And the closer we can come to entropy, the better our encoding is. So we have now, the entropy gives us a way of measuring how good an encoding is. Okay, so if I tell you that the average number of bits that I send you is less than the entropy, what should your response be? I'll buy 10. Your response should be deep skepticism. Because if on the average I'm sending less bits than are needed to resolve the uncertainty, according to our information formula, okay, there must be some things I'm not resolving. It's like sending 5 bits for the roll of 2 die. There are some situations that I can't encode in the amount of bits I've sent you, so there'll be still a little bit of uncertainty left. So in general, if anybody tries to sell you encoding that has fewer bits on the average for each message than the entropy tells us, don't buy it. This isn't good. On the other hand, if I'm on the average sending you more bits, is that good, bad? Well, the answer is it's all right. Okay, it's making do. Perhaps there's a more efficient encoding, so this might be slightly inefficient, but there's nothing wrong with this. Of course, the best solution is if I can come up with an encoding that exactly matches the entropy. And a lot of modern communications and coding theory is running around in searching for codes where the encoding that is generated by the encoding machinery, by the coding machinery, the string of bits that comes out, actually comes very, very close to matching the information content of the message received, of the message trying to be sent. So when you get your when you take pictures and speak into microphones and it all gets digitally encoded, there's a lot of very high tech in there that's trying to preserve the information content of your picture or your speech, okay, in a way that's still good for us, okay, that comes as close as possible to the most efficient we can do. Okay, so encodings. An encoding is just, I want to match a bit string to a particular set of messages I want to send, and now I want to do a good job of choosing the right bit string. Okay, so I'm going to try out different examples, and you're going to have to work with me here to figure out which ones work and which don't, and why not. So the most obvious type of encoding is one where we use a so-called fixed length encoding. Right? I'm going to choose, in this case I have 4 things to send, I'm just going to choose a 2-bit pattern, and I'm going to use all possible variants of the 2-bit pattern, 0001, 10, and 11, okay, to encode each of the 4 possibilities. So how would I encode the string of ABBA? This used to be, you know, God help me, I listen to ABBA every morning when I am in the gym. Okay, there's something about, you know, but you're all going, ABBA? Who's ABBA? You know, so, right? No? Anybody here know who ABBA is? Oh, yeah, my parents used to hum it in the car all the time. It was annoying. Okay, how do I encode ABBA? What's the encoding of ABBA using this particular mapping? Help me out. Someone be brave. Okay, everybody understand the process? I just, you know, A, I encoded that using the encoding. B, I encoded that. Is it easy to go the other way? If I sent you this string and I gave you that table, could you take that bit string and turn it back into the original message? Sure, you just take groups of 2 bits and go look them up and voila, you'd be done. Let me give you a different encoding. This is called a variable length encoding. Okay, how would I encode ABBA? Well, it would be 0, 1, 1 for the B, 1 for the B, and 0, 1 for the A. Decoding is a little bit trickier. I have to actually follow a more systematic process. I basically consume bits from the string. So I pick up the 0 and I say, well, 0 doesn't match any of my encodings. So then I take the next bit and I say 0, 1, and I say, oh, okay, 0, 1, oh, that matches an A. Right, so I sort of consume the bits from the string incrementally until I get a match with my table, and then I write down that symbol, and then I take the next part of the string. Okay, so variable length encodings. I can't jump into the middle of a variable length encoding. Your digital TV is uses variable length encoding. You know how when you switch a channel, it takes a second for the picture to appear? It's not like instantaneous. There's this decoding. It's basically, it has to wait until it gets to the boundary of one of the frame encodings, the so-called iframe, in order to start the variable length decoding process from it knows, you know, where in the beginning. If I just start in the middle here, you know, I don't know whether I'm, you know, eating part of a one character, you know, the encoding for one character, and I'm trying to interpret it as a different character. Well, that seems pretty easy. How about this? This is even better. This uses fewer bits, right? So these 2 are good. Check, check. This uses fewer bits. So it must be a better encoding. So how do I encode ABBA? 0, B is 1, B is 1, A is 0. Ta-da! What's wrong? There's some chuckles. Yes. What's wrong? Yeah, it turns out that decoding is encoding went really well. In fact, 4 bits, I'm ready to call up, you know, Rupert Murdoch and tell him I'm going to save him a lot of bill on his network, a lot of money on his network bill because I can encode things very efficiently. Always send to 0. That'll take care of it. In fact, just tell the user that it's always 0, and they don't even have to tune in. And obviously, there's sort of a notion of saying, well, I can't really decode that into Game of Thrones, right? I mean, that's, you know, and so there are some issues here. The thing is, there's some ambiguities. So I can decode this message as ABBA, certainly. I can also decode it as ABC or ADA, depending on how I group the bits. Right, so the trouble is that this 1 is either B or it's the start of the encoding for C or D. And that's where the trouble was. It's not an unambiguous encoding. Mostly we're interested in unambiguous encodings. How do I tell if a coding is ambiguous or unambiguous? Secret. I build a binary tree showing me this. So here's I've got a suggested encoding here, the second one on the page before. Oh, I should probably, just to make sure everybody knows, this is a no-no. This encoding. Okay. So let's build a tree. So I'm going to start at the root of the tree, and I'm going to use the zeros and ones to sort of help me build out a binary tree. So B was a 0. A is 1 followed by a 1. C is a 1 followed by a 0 followed by a 0. So this is C. And D is a 1 followed by a 0 followed by a 1. Oops, I forgot to write A. So if I look at that binary tree, and I look at that, and I say, notice how all the labels are on the leaves? That's what I'm looking for, right? If there was an interior, if I had labeled an interior node, E say, right, then I would have an ambiguity, because when I see this first one, I don't know whether I meant E or I was on my way to A or D or C. Right? So if you do this binary, if you take a proposed encoding, you build this binary tree, and all of a sudden you end up with labels in the middle of your tree, the encoding is not unambiguous. Do androids dream of electric sheep? Here's an electric sheep. You can tell he's electric. He's sending a message. What's the message the sheep is sending? It's an American sheep. I've been told that other sheep in other countries say different things. So. But this one's from the heartland. Probably voted for Donald Trump. Okay. Sorry, no politics, no politics. Get myself into hot water really quickly. Okay. So a fixed length encoding is the binary tree, all the leaves are at the same depth. So that means we're using the same number of bits to encode everything. Okay. And in fact, the entropy of a fixed length encoding that has n leaves like that is basically log base 2 of n. Whoops, sorry. I'm new at this tablet game, so I keep pressing erase when I shouldn't. So bear with me, I'll get better. Okay, so 4-bit binary coded decimal. So I'm on to encode the digit 0 through 9. BCD is binary coded decimal. So we have basically log base 2, there's 10 digits, right? And that's equal to 3.322 bits of information. And what we discover is that fixed length encodings are often a little efficient in terms of the entropy. In other words, fixed length is handy for lots of, sort of technical, easy engineering reasons, but we pay a cost in the entropy, an entropy cost in the efficiency of our encoding. Let's see, there are 94 printing ASCII characters, so that's equal to 6.555 bits, but we use a 7-bit ASCII to sort of represent those. Okay, so that's one possible, so we often use fixed length encoding for numbers and certainly for letters when we don't have any information about the probability distribution for either. Something that we really want to encode a lot of is integers. And you have a bunch of slides. We're going to cover, yes sir?
Hi, so I was working it out, and so I found that it's possible to have unambiguous encoding if you have things that are not in the group. Like, if you're only encoding A and B, you have AB10 and BB1. That is unambiguous, but really inefficient. Are there like small edge cases where it's possible to make efficient encoding for the things not on the node? So for the things not on the group?
I'll have to think about your example. So the short answer is, not that I know of, but let me go try your example and see if I can figure out the right answer I should be giving, but can't think of in real time. Post it on Piazza, and then that'll help me jog my memory to give you a good answer. We're going to discuss this tomorrow in recitation. So there's a bunch of slides that I am going to skip over. Okay, and just move on to the next interesting topic, which is variable length encodings. We already saw one of those. Okay, so if you're interested in how to do numbers, come to recitation. If you look in the topic videos section of the website, you will discover, if you want to see those slides presented with a wonderfully narrated, beautifully scripted description of what each slide means and is trying to tell you. Go to the topic videos, find the right topic video that says, Duke's Supplement or something like that, and play it. It's probably 5 minutes long, and you too will know what those slides are. Or come to a recitation tomorrow and we'll work out a bunch of examples. If you're like me, I prefer working things out. That gives me a better intuition right away. So, but if you like watching TV, there is 6004 TV available 24/7. Streaming. You can binge watch the entire course this weekend. Good luck on the exams. Okay. All righty, variable length encodings. Here we are. So what I want to do is to match the length of the data. We have some data we're trying to encode. Let's say an English message. Let's say the sentence that says goal. And I want to send that to you in the most efficient way possible. Obviously, if I'm using a 7-bit ASCII encoding, I could just multiply the number of characters by 7 and I'd be done. Okay. But English isn't that way because there's some characters in English that occur more frequently than other characters. E's are very common, Q's hardly ever. Okay, and so to be more efficient, you can imagine to reduce the number of bits I have to send you this or other messages, I would probably want to send an E using a shorter number of bits because there's a lot of E's. And I want to send Q's using a long number of bits, okay, because there are hardly any Q's and it almost doesn't matter how much a Q costs to send. And so what I can do is use that to build an effective variable length coding that takes higher probability things and uses a shorter encoding, a shorter encoding from my variable length code, and lower probability things will use a longer encoding. Okay, and we call these encodings variable length encodings. So the goal is just to reduce the average length of a message. Okay, so we've seen this. Here's my characters. And in fact, the tree that I gave you, so B is the highest probability. See, it has probability 1/2, and we've given it the shortest encoding. C and D are the lowest probability here, and we've given them the longest encoding. So we're following our own rules. And in fact, we have a tree here that we came up with. It turns out this is the optimal tree when encoding things one at a time, and we'll talk about how to get optimal in just a second. Alrighty, so here we go. Let's decode this message. So 0 is B, 100 is C. Right? I just start at the root each time and just use the next digits as sort of a path name to get me to a leaf. Then I go back up and do again. One more. 11 is an A, so forth and so on. Got it? Okay, the expected length of this encoding. What is the expected length of this encoding? Well, with probability 1/3, the encoding has a length 2. That's the encoding for A. With probability 1/2, it has an expected length of 1. With probability 1/12, it has an expected length of 3. And in fact, there's 2 of those. Right? This is equal to 1.667 bits. That's the expected length of the encoding. So just to summarize where we've been, if I had been using 2 bits to encode each of the 4 choices, if I was going to send you 1,000 symbols, it would have cost me 2,000 bits. 2 bits for each of the 1,000 characters. Good? Using this encoding, how many bits will I send on the average? 1667. What did entropy tell us was the minimum number of bits I have to send? I think it was 1626. That was the entropy calculation we did back when we did the entropy calculation on these probabilities. Okay, so you can sort of see that we've done pretty well. We've improved the average length of messages for sending 6004 grades, okay, for each class. On the other hand, we haven't done as well as we could. Could we build a better code? So there's an algorithm called Huffman's algorithm, named after David Huffman. And this is a wonderful MIT-ish story. He was a master's student here at MIT. He was taking a course from Bob Fano and Joe Wozencraft. They were just a course. And so they gave us a homework problem. Come up with a way of doing this optimal encoding. I'll give you probability stuff. So he went home and he came up with this little algorithm. and he came back. Huffman algorithm, I would say, by the way, Huffman codes are used in pretty much every digital encoding scheme in the world. Okay, everything you do has a Huffman code at the base of it. And so this was just, oh yeah, a homework problem. I came up with a neat little solution, right? Needless to say, the professors were impressed, and he managed to get a master's degree out of it. So, not a PhD, but he had to go do something better for a PhD. Alrighty, so let me show you how Huffman's algorithm works. It's described in words there. I want to use it on the little message we're doing. What I'm going to do is to build my encoding tree from the bottom up. So I'm going to start with the least probability symbols. So what are the two symbols that have the least probability? The smallest? C and D. And I'm going to do it like this. I'm going to say C and D, and I'm going to give them a little tree all to their own. And I'm going to say the probability associated with the root of that tree is 1/6. So I've got a proposed encoding for those two. I'm not done yet. So now, given that little tree and the other two symbols, which two things have the smallest probability of the options I have left? So I have this little CD subtree, and I have A and B. Which two things have the least probability? A and the subtree. So I will build a little subtree involving those. A and the subtree, A. And that has probability 1/2. And if I add a third for the A and a 6 for the subtree. Okay, and now what's left is B, so not a lot of choices to be made. So that's probability 1. So this is 0, 1, 0, 1. So I've sort of systematically built a binary encoding tree. Right? We'll try some examples in section tomorrow. You should try lots of different examples to get a feel. Depending, either you're creating new subtrees, or you're combining subtrees, or you're combining a symbol in a subtree. It all depends which two things have the lowest probability at the moment. The idea is we're taking the things that have the lowest probability, which means they should have the longest encoding, and we keep sort of putting them farther and farther down in the tree as we build the tree up. So things naturally that have low probability will end up deepest in the tree, and that's what gives us the optimal encoding. So it's optimal in the sense that you can't come up with an encoding that on the average will send fewer bits. There's many equivalent optimal encodings. Like obviously you could change all the 0 and 1 labels, and that would be okay. Okay, how do I do better? Well, I'd have to encode sequences. So suppose I took pairs of grades and then think of that as the message I send. Instead of single grades, I always send 2 grades at a time, right? And I go off and I compute the probabilities and I build a Huffman code using that tree. Now I'm down to 6.46 bits on the average to send 1,000, just the expected information length. Okay, and in general, as I think of larger and larger and larger messages, I get closer and closer, larger and larger and larger codings. I come up with encodings that much more closely match the exact bit length of the string, of the encoding string, with the exact information content. So I approach the entropy bound. Want to read more? Read up about LZW, the compression algorithm we all use. It's inside of 7-zip and B-zip and B-zip and zip-zip and... I'm surprised Zipcar hasn't been sued by whoever it is. There's some company that owns Zip. Yes?
Does encoding a sequence necessarily mean that your encoding will be more efficient?
There's not a guarantee. You could obviously do a bad job. But in general, encoding more and more characters and then thinking of all the possibility for that big character chunk gives you many, many more things you're encoding, and then you're able to much more precisely choose the lengths of strings to match the exact probabilities. So in a say, it's not a question of longer, it's just the more choices you have, the better you are to match the encoding to the information content. Okay. Yes, sir? Let me just see if I can rephrase what I just tried to say. So what I have here is, you can see I have a much wider range. I have many more things to encode, right? And so what that's going to give me is an opportunity, as I carefully build think of the Huffman algorithm, I'm able to make much better choices about which two things should be together because they have very close to the same information content. And so I don't have these sort of quantization problems, right? So the probability that A was a third I mean, I'm either going to encode it with 1 bit or 2 bits. When I really, to get the right thing, I really want to encode it with 1.5 bits. And so the problem is that I'm trying to look for ways to get closer and closer and closer. So these numbers get smaller and smaller and smaller. The difference between these probabilities and 1 over 2 to the n for some n, okay, gets very small. So the inefficiency of my encoding improves. Huffman always does, the perfect encoding is 1. You always match the entry rebound when all the probabilities are 1 over 2 to the n for some n. That makes sense? Yeah, think about it. Okay. What about errors? I'm sending you lots of bits. What happens when bad things happen to good bits? Here's Bob and Alice talking to each other. They seem to be talking in code. They're sending the results of a coin flip. This is not the most fascinating conversation, but it's what you get when you date somebody from MIT. Heads. Oh, thank you, Bob. Same to you. Okay, so Bob is sending zeros and ones to say what his encoding is. What happens if there's some noise on the wire and what poor Alice receives is a 1? Okay, so she thinks that Bob has actually said tails. What I'd like to do is to think a little bit about what we can do to solve this problem. And it turns out that we have a handle on this if we think about it a little bit. So let's put on our thinking caps and see how we can solve what's called the error detection and correction problem. I send you a bunch of bits and you want to be able to say, nope, those are bogus, or, well, there was an error, but don't worry, I can figure out I know what you meant. I'll correct the error. How we can choose encodings that let us do that? So the key to figuring out how this works is the notion of Hamming distance. Should I tell you the story about how Hamming was a student? No. So information science really got its, a lot of the early developers of that were here at MIT, including Shannon for a while before he went off to Bell Labs. Okay, so I look at these 2 bit strings. In how many positions do these bit strings differ? There's 2 bit strings, they're the same length. Well, I go look through here and say, well, I see they're different here, and they're different here. So those 2 bit strings differ in 2 bit positions, right? So the Hamming distance, which is a wonderful $50 word for a very simple concept of how many bit positions are different in the 2 strings. So the Hamming distance of this string and this string is equal to 2. Okay, Hamming distance. We used to have, before the thought police got to us for using Dr. Seuss slides, we had this picture of this guy with ham and, ham and eggs and, but we're no longer allowed to show that, so. Anyway, Hamming distance has to do with the distance, the number of bits that change from one string to another. How does Hamming distance tell us about how errors work? Well, the Hamming distance between a valid binary code word and a word with a 1-bit error. In other words, I take some string of bits and there's an error. The Hamming distance of the thing that's been received is Hamming distance 1 from the thing that was sent. Okay. So a single bit error basically produces a corrupted code word, okay, a corrupted bit sequence, a message sequence, okay, that has a Hamming distance of 1 from the one that I originally sent. The trouble with this stupid encoding is the 2 code words, 0 and 1, had a Hamming distance of 1 apart. So a bit error took us from one valid code word to the next valid code word. Okay, now that we understand what bit errors are doing, this seems like a very bad encoding. How do we get a better encoding? I left room for exactly n equal 1 zeros and n equal 1 ones. 0, 0, and 0, 1. Okay, so we sort of look at that and say, okay, how is that better? What happens if I corrupt the heads message with a single bit error? Well, I either get 0, 1 or I get 1, 0. These are single bit errors. And actually, I get the same thing if I corrupt a tails message. If you got 0, 1, you were Alice and you were listening to Bob sweet talk you and you were saying, Bob, say that again, 0, 1. Okay. And you said, what could you deduce from getting a 0-1? You could deduce that there was an error. There was a 1-bit error. If there was a 2-bit error, you're out of luck. Okay, but you could deduce the fact that there was a 2-bit error. Excuse me, there was a 1-bit error. So you can at least detect 1-bit errors. This is called parity. Okay, so there's a notion, in this case we were using what's called even parity. We added enough ones, we added one digit to the string so that the total number of ones was even. Okay, so there's a notion of a parity check. So I've done even parity, so there's an even number of ones in this string. There's 1, 2, 3, 4, 5. So this one has an error. This one, okay, well, we'd like to say it's okay because it has an even number of ones. It turns out that it actually has 2 bits of error in it. So parity won't help us detect multiple bit errors, but it will help us detect single bit errors. Okay. Suppose I wanted to detect multiple bit errors, and this will be my last 12 seconds. The answer is, what I can do is to use a bigger Hamming distance. So the Hamming distance here is 3, and that means that I can detect 2-bit errors. So I can detect 2-bit errors. So forth and so on. And we can even do error correction, and we'll cover that a little bit tomorrow in recitation. So I'm going to stop there. Recitations, Wednesdays and Fridays. If you don't have a recitation assignment, feel free to look on the website. It tells you what information you need to send us, and we'll find you a recitation to go to tomorrow. See you soon. Hello. I'm going to physically unconnect myself while we talk.
Okay, absolutely.
Yes, sir.
I was looking to understand entropy a little bit more.
Okay.
I wasn't completely sure of the concept of how entropy related to a sum of the information. The sum over the probability.
It's a weighted sum. It's really just, we're just computing the expected value.
Okay.
Right, so entropy is saying if I send you a zillion messages, on the average, how many bits will I send you? Entropy is just telling us that.
Okay.
So it was a way of sort of measuring us, the average cost of sending a message using well, in this case, it tells us how many bits we have to send because the entropy is being calculated on the actual probabilities involved.
Okay, so it's telling us the least number. Well, no.
Yes, it's sort of giving us a lower bound. If we send less, we're not sending enough. If we send more, we're being inefficient.
Okay.
Is that good?
Yeah, that's good.
Okay.
And that was what the lower bound was, the entropy.
That's what 1662 was the entropy we had calculated, some slides before.